Today we are starting Unit 3, and we're going to take a look at the first two lessons together, which is all about exploring circles. So we have a couple of questions that are being combined from Unit 1 and Unit 2, from Lesson 1 and Lesson 2. And we're going to be looking at these learning goals today. First, we're going to look at the difficulties in measuring quantities in a proportional relationship accurately, and accurately is going to be the key to what we talk about today. We're also going to identify parts of a circle and describe the characteristics that make a shape a circle. So let's look at our first question. This says the perimeter of a square. Here is a table with some measurements. They are also graphed to see if there is a relationship between the perimeter of a square and its diagonal. What do you notice about the points on the graph? So here, most of the work has been done for us. Now, if we had a square, and it looks like we have multiple squares here being shown in our table. If we're measuring the diagonal, we would be measuring the distance between diagonal points here. Now, if you remember, a square has four congruent sides, four equal side lengths. So if I were to measure this diagonal, it should be the same as this diagonal because all of the sides are the same length. The other thing that was measured was the perimeter. Remember, the perimeter is the distance around the outside edge of the shape. So around all four of these side lengths, which again are the same length, but it would be 4 times greater. Now, if this is all measured here in the table of these different squares, so we can assume that these different squares have different side lengths when they're compared to each other, but of course to be a square they all have to be the same. So we can see their measurements, and it looks like most of their measurements have a decimal, go to a decimal place. They were measured in centimeters, and so our measurements are not whole centimeters here. So when these were put on the graph, see how they don't nicely line up with the grid markings here on the graph because they are kind of falling between those whole numbers. But we're asked, what do we notice about the points on the graph? Well, it looks like they're forming a straight line. It appears like I could connect these points pretty much into a straight line. And it also looks like I could extend that to the origin there. Those are the two qualifications for being a proportional relationship. So it appears that we have a proportional relationship here. Of course, that would mean we should have a constant of proportionality. So if we were to take our y value, which is perimeter here, if we were to take our y value and divide it by our x value, we should get a constant of proportionality. Now, if we look at the specific measurements here on the shape, and we were to divide 16.1 by 5.7, what we would get is a long decimal. And we could round that, let's say, to the hundredths place, which would equal a k value, a constant of proportionality of 2.82 if I round to the hundredths place. I would get the same thing for square b, but it actually has different values after the hundredths place, but based on how we would round, if we rounded to the hundredths place, it would be the same constant of proportionality. But now if I drop down here to square g, and I divide 6.2 by 2.2, I would get 2.818. And that actually continues as well. If we rounded to the hundredths place, this 81 hundredths would round up to 82 hundredths. So it would be the same, but there's minor differences between all of these k values, even though they're about the same, and even though they appear to form a straight line here on the graph. Now, because this was measured, I think we can say it is a proportional relationship. between the diagonal of a square and the perimeter of a square. These k values, if we divided all of them out, are definitely close enough to say it's a proportional relationship. And the error in our numbers is because of rounding, or it could be because of measurement errors, looking at that ruler, trying to decide which marking its length would be closest to. So I believe we have a proportional relationship here. If we look at the next one, we're comparing the area of a square. So we've got our same squares here. I believe this is the same diagonal measurements that we had on the previous activity, but now we have the area of the squares calculated for us. So let's see if see what we notice here. So if we look at the graph, looking at all these data points, this doesn't look like a straight line anymore. It looks like a curved line. It looks like it still might extend to the origin, but it's not checking that other box of being a straight line. It appears that we don't have a proportional relationship for this one. We could talk about constant proportionality again. So we have area is our y-axis, our y value, and the diagonal is still the x-axis. If we divide y by x to get our k value, our constant of proportionality, for the first one here, we'd find that it's 1.1 for square A. For square B, it's 1.71. And for square C, again, I'm doing y divided by x. So for square C, it's 9 divided by 4.3. That would be 2.09. Now, these do not appear anywhere close to one another. They're very far separated from each other, which would prove, again, that we don't have a proportional relationship. This big of a difference, one whole amount difference between square A and C for the constant of proportionality, is way more than we would say is allowable, like the last example, where it's just slightly off because of maybe a measurement error or rounding some numbers. Okay, so no proportional relationship here. And trying to graph this, or the previous question, would still be difficult because all of these decimal amounts are going to be very hard with an interval here on the graph that's separated by 2 here on the x and 10 here on the y-axis. That's just too spread out. It's too inaccurate to get good data for what we're trying to show here. All right. Let's move on to the last activity on this side of the handout. It talks about sorting round objects. What are some characteristics that all circles have in common? So take a look around the room, think about some circular objects, and let's make a list of those different things. So of course, circles are round, so it has a round edge. There's no angles, would be another way of saying that, like most of the shapes that we deal with. It's got to be a closed figure, and closed means that it connects. It doesn't have a gap in it like a horseshoe would. So it's a closed figure. Also, circles are two-dimensional. You would think a three-dimensional shape similar to this would be a sphere, but that is definitely not the same as what we're referring to here when we talk about a circle, a flat surface. Okay, the next part says, what are some ways that you can measure the actual size of the circle? And this is going to be very important in our next activity. So if we have a circle, some things that we can measure, because we don't have a traditional side that we can measure like we would a square or a rectangle. But we do have, if we were to choose a starting point, we could measure this rounded edge from the beginning all the way around to the end of it where it reconnects. And that would be a measurement that we could take. That would be called the circumference. We could all circles are going to have a center point. So we could measure through that center point from one edge to the other, and that would give us the diameter. Or we could just go from the center point to the outside edge, which is called the radius. One more thing that we could measure with a circle, being that it's two-dimensional, is we could find the area of this circle, which we'll talk more about later on. For this activity, and I know the images on your copy are a little darker, we're going to be talking about 3 real-life circles. So we have the wheel of a bike. This label is cut off, but this is a glow necklace, the kind that you'd crack and then put around your neck and have that glowing a different color. And then a yo-yo trick. If you can see on mine here, this person is standing holding a yo-yo on the extended string, and it's showing the path of the yo-yo as it swings around the person. So kind of making a large circle around her. So it says, Priya, Han, and May each measured one of the circular objects listed here. Priya says that the bike wheel is 24 inches. Han says the yo-yo trick is 24 inches. And May says the glow necklace is 24 inches. Do you think all these circles are the same size? All right. Now, it certainly appears so if they're getting measurements that are all the same length of 24 inches. But just in what we know about real life, hopefully know that a bike wheel is not going to be as big around, or it's going to be way bigger than a glow necklace around your neck. And both of those are going to be smaller than what we can see here. This yo-yo trick is extending pretty big. It's going to her knees and then well above her head, which would be much larger than a bike wheel. So, do we think that these circles are the same size? I think it's very safe to say no. Now's the important part. What part of the circle did each person measure? So we're going to believe that these 3 people measured 24 inches correctly, but they must have measured different parts of the circle. And going back to what we just talked about, there's all kinds of different things that we can measure on a circle. So let's talk about that measurement first. So 24 inches, that's equivalent to 2 feet, 2 rulers. A ruler, a standard ruler, is 1 foot long. So imagine what that would look like. That might be about the length of your forearm from the tip of your fingers to your elbow, will be about 2 feet. All right. Now, if we look at this bike wheel, thinking about what could be 24 inches on the bike wheel, so about the length of your forearm, I don't think we could stretch around this bike wheel 24 inches unless it was a very tiny bike wheel. What this seems more like to me would be the distance across the bike. And remember, the distance across the bike going through the center point from edge to edge is the diameter. So let's label that as diameter. Now let's talk about what Han said. So the yo-yo trick is 24 inches. All right, this is the biggest circle that we're looking at compared to these 3. So it's definitely not going to be the distance around or the circumference. It's not even going to be the diameter because that would be too much. Think about the height of this person. This person's probably 4 to 5 feet tall, and the circle across the whole thing is at least 4 to 5 feet then. So what we must be talking about is from the center of this circle to the outside edge, or half of the diameter, and that would be called the radius. Lastly, May says that the glow necklace is 24 inches. All right, picturing a glow necklace around your neck, this measurement around the outside, could that be, if you had a yarn, a piece of yarn or string that was the length of 2 rulers, 2 feet long, would that wrap around your neck? Yeah, I think it would. And that would be the measurement of circumference. Okay, now let's look at some key vocabulary quickly. And this is going to be incredibly important. So please write this down. Please learn these words and get used to using these words, because every situation that we come across here for most of Unit 3 is going to contain one or more of these words. So going back to how we just described these 3 images, it says the distance from the center of a circle to any point on the circle. That was what we used to describe the yo-yo trick. The distance from the center of the circle to the outside, that'd be like the length of the string of the yo-yo, was called the radius. So let's record that. Then a line segment that has endpoints on a circle and passes through the center. Going back, that was the bike wheel. That 24 inches, the 2 feet, went from one edge of the wheel through the center axle to the other edge of the wheel. All the way through, all the way across that wheel is called the diameter. Then it says the distance around the circle. If you imagine the circle as a piece of string, it's the length of the string. And this was talking about the glow necklace. So the length around the glow necklace. This is really like the perimeter of most figures, because perimeter is the distance around that outside edge. We just call it something different with circles, and that is circumference. All right, now we do have a formula for circumference, and we will talk much more about this with our next lesson. But the formula for the circumference of a circle, one that you're going to need to know, is circumference equals pi times diameter. Now that might sound incredibly foreign to you. You may have heard of pi, and we're not talking about the delicious baked good. We are talking about a mathematical number here, but we will talk much more about that tomorrow. I just want you to have this here in this important notes about circles, and it will all kind of come together as we continue. We won't be using that today. But the last thing here is a shape with a radius r with center O is the set of all data points that are a distance r units from O. That's an incredibly complicated definition for what a circle is. Remember, radius goes from the center of the circle, which here is O, out to the outside edge. And this goes around the entire outside edge of the circle. All right, let's continue. We're going to look at 4 examples here that I'm going to do with you. Then I want you to try the other 8 on your own, because they're just a mirror of what I'm going to be showing you here. So please pay close attention. It says, what is the radius and the diameter of each circle? Now, based on our definitions, remember, the radius goes from the center of the circle out to the outside edge, and the diameter goes all the way across the circle. So, if we have one radius again from the center of the circle to the outside edge, that will equal half of the diameter. And hopefully that makes sense, because if I were to take this radius in circle A, which is 5 millimeters, I'm going to go ahead and record that. And if I were to take that one radius and extend it to the other edge of the circle, now I have the full diameter. So one radius is only half of the diameter. 2 of the radius will equal the full diameter. So I'm going to add that to my notes here. 2 radius equals 1 diameter. So the diameter for circle A would be 2 radiuses, or 10 millimeters. For circle B, look at what we're shown here on the diagram. 12 centimeters is our measurement, and that is representing all the way across the circle from edge to edge through the center point. That's our diameter. Our diameter is 12 centimeters. And our diameter is 2 radiuses. So if I want to say the length of one radius, I'm going to need half of the diameter. Half of the diameter would be half of this measurement. We're only going from the center to one outside edge, and that's going to be 6 centimeters. All right, for circle C, we're given, this is half from the center of the circle to the outside edge. This is our radius. Our radius is 9 meters. To extend across the whole diameter of the circle, we need to double that for 18 meters. And here for circle D, we are extending across the whole circle already, which is 16 kilometers, and our radius will be half of that, 8 kilometers. All right, please use this as a model for the other examples that I want you to try here on your handout for today. Again, it's just finding radius and diameter of a circle. Please get familiar with that vocabulary very quickly, because we're going to be using it a lot, and continuing tomorrow where we talk more about circumference.